Hello, good morning. Start recording. Okay, good morning, guys. So today we will continue from where we stopped last week. So last week we look at the soil shear strengths, and we find that some soil can fail due to failure between the soil particles, and that's why the shear strength is important for us to know. And the shear strength of the soil depend on four parameters or four elements: stresses, or the effective stress of the soil, the density of the soil, whichever dense or loose soil, and the friction angle, or phi, and cohesion, we can give it the symbol C. So these are four parameters we are looking at when we calculating the or determining the shear strength of the soil. So this was the last part we discussed last week, and today, what is the shear strength formula, or how we can calculate the shear strength? The shear strength will be calculated using the Moore-Coulomb equation, which is tau equal to C plus sigma tan phi, where T is the cohesion, sigma is the stress, and phi is the friction angle. So cohesion and friction angle, this the two parameter we mentioned in the previous slide for the like the two element from the four element of calculating the shear strength, and here is the stress or the effective stress. Okay, so again tau equal to C plus sigma times tan phi. This is our formula for shear stress, where tau is the shear stress or strength of the soil. Okay, then the next step will be we can know the stress, but how can we find C and phi? C, the cohesion, and phi, the friction angle, can be determined using some laboratory tests and some correlation between like some tests you give the number of blows to penetrate or something like that, so you can find a correlation between some of the result of tests or test results, and from the test result we can find the shear strength of the soil. And the third one is some guessing or engineering guessing or educated guessing. So based on the information we have, we can make some assumption or guessing for the shear strength of the soil. Okay, and again on this diagram, this is the shear between the particles, and we are looking at the shear strength of these particles. Okay, so this is how the shear strength is calculated, and here is some of the tests that are used for calculating shear strength. So we have direct shear test, and this is the machine used for that. Okay, and here is the about. And here is sorry. Okay, so here is the machine used. Okay, and here is the apparatus using for calculating the shear strength. So we have to fill this box with soil, as you can see here. So here is the illustrative figure. So we put the soil here in this area, and then this box has two move bar, so we can move one bar to the right here in this direction, and the other one move to the left. So we have two forces, one in this direction and one in this direction. So this soil or this sample will be under shear, okay? And we have to apply like normal force from the top. So we have shear force and normal force applied on the soil, and using this test we can find the shear strength of the soil, tau. So this test will be helping us to find tau directly in the lab. Okay, and here is the data we got from the test, direct shear test. So we will have shear stress on the vertical axis and horizontal displacement in millimeter by on the horizontal axis. So the vertical axis shear strength or shear stress, and horizontal displacement on the horizontal axis. And we have here 3 samples or 3 tests. So we are picking the peak of each sample. So we have 3 peaks here, like peak number 1, peak number 2, peak number 3. And then from this test, so all this data in this figure come from the test. So we have 3 samples, for example, and we plot the shear stress we got and the horizontal displacement we got in one plot. And then we pick the 3 peaks point, for example, if we have 3 points. And then the next step is to draw a diagram between shear stress and normal stress. So shear stress tau on the vertical axis, normal stress sigma on the horizontal axis. As I told you, we have applied some normal force from top or normal stress, and here we have shear force or shear stress. So we can draw a relation or a diagram between shear stress and normal stress. So this 3 points are peak number 1 or peak 3 based on the diagram we have. So this is the 3 peak point we got. Okay. So using these 3 points from the test, we can connect them with a linear relationship or a linear line. So this line is linear relation between the 3 points. So from our test, it will be these 3 points will be almost on one line. And from this line or from this plot, we can find how much C and phi. So what is phi? Phi will be the slope of this line. So phi or the friction angle is the slope angle. And what is C? C, as you can see here, in some cases, we will have an intersected component from y-axis. So C will be the vertical component on y-axis due to intersection between our linear line, and y-axis. Okay, so this is one case. So our figure again, our diagram. Sorry. So this is our diagram. We have 3 big points. As I mentioned, this is big point 3, big point 2, big point 1. So we have 3 big points and we connect them with a straight line. This line will have a slope phi and an intersected part and vertical component on y-axis. So phi of the slope angle will be the friction angle of our soil, and C will be this vertical component. Okay, so do you know now how to find C and phi? So C and phi will come from this direct shear test. C for cohesion and phi for friction angle. Okay, so for this case, for example, the test we have done, I will highlight it. This diagram. So this yellow one is for cohesive soil because it has C and phi. But for cohesionless soil, like sand, what will be the case? The case will be different, and we will have another case. For example, we have connected our 3 point. Let's say we have point 1, 2, and 3. If you look at case 2, the green one here, what you will notice that we will have phi. Okay, so we will have phi, but this axis will intersect at the 0 and 0 point. So if we look at this case, we will have value of phi, but C is 0. So if we have this case, what you expect? Cohesive soil as well, or other type of soil? This soil is cohesionless soil, or we can call it, or we can mention it is sand or gravel. So for sand and gravel, the value of C is 0 because there is no cohesion between the soil particles, and the linear relation will pass through 0. But for cohesive soil, we will have value of C and value of phi because for clay and silt, we have cohesion between the soil particles, so that's why we should have value of C. Okay, so this is how to determine C and phi using the test in the lab. Do you have any question about that? No? Okay, if we look at this table, so this table give us some values of the C and phi parameter. So C cohesion and phi friction angle. Okay, in this table we have angle of shearing resistance or phi. So for loose gravel with sand content, we will have the angle between 28 to 30 degree. And for example, if we have loose and fine silt here, we have from 28 to 30 as well. So what will be the difference between these two? The difference between these two is here phi has a value, but C will be 0. Here, because it's silt, so we have value of phi, but C will have a value because this is cohesion or cohesive soil. Okay, because it has some silt. Okay, so this table can be found in this source, the Australian Road Bridge Design Code. So you can have a look on that. And here is the values of C and phi for some soil types. So we have soft and firm clay. C will be between 0 and 5 kPa, and phi will be between 17 and 25 degrees. For example, here for rock controlled fill, C from 0 to 25, the degree of angle of friction or phi will be between 36 and 43. These numbers or these values just to have some background or some knowledge about the values of C and phi, but we don't need to keep this in mind, just to have some background on that. Okay. So if this required in an problem or in the exam, so it will be given to you. Okay. So don't worry about how much is the information given, but just to understand the idea on how to find the shear strength in the lab and what is the range of phi and C for some types of soil. Okay, this table can be found in Australian Standard 4678 for earth retaining structure. So you can find the values of C and phi in this standard. Okay, so now we can have a short activity about how to this will be for revision on the effective stress on soil that we have done last week. So I will solve it with you, so you don't have to like spend time on that. So for example, this one here, I will just add. Okay, so we have in this example, just to read the example, we have to calculate the effective stress at the bottom of soil layer shown below. Assume that the water table to be located at 5-meter depth. So we need to find the stress at any point here, somewhere here, whatever. So this is point A, and the water table is in the mid-high here, mid-height of the soil layer. So this is our water table at 5-meter high. Okay, so we need to calculate the effective stress, sigma dash, at the bottom of this layer. And then the next stage is to find the effective stress if the water table rises to the top of the soil layer. So firstly, we have, so number question 1A. So we have a soil layer. The total height is 10 meter. And we need to find the stress at point A. The soil density equal to 18 kilonewton per cubic meter. And it was given to us that case 1, or the first case, this is the water table at height 5 meter from top or 5 meter from bottom. So we need to calculate sigma dash at A. Just to remind you, what was the formula for sigma and sigma dash? Sigma, the total stress, was equal to sigma dash, the effective stress, plus the water pressure. So sigma equal to sigma dash, effective stress, plus U, or water pressure. So from this formula, sigma dash will be sigma minus U. Sigma dash at A will be sigma at A minus U at A. So the effective stress equal to total stress minus water pressure at A. This is the formula we are using. And if we look here, so what is sigma A? If you remember, the total stress sigma A at a point here will be equal to, can anyone help me to do that? Will be gamma bulk soil or gamma soil times the height of soil, Z soil or H soil. Okay, so we can call it H soil to make it easier. So the total stress will be gamma times H soil. So how much gamma soil given to us? 18 kilonewton per cubic meter. How much the soil height? The soil height of the layer height, the total height of soil is 10 meter. So this will be 180 kilonewton per squared meter. This is the effective, sorry, this is the total stress. So the total stress is 180. For you, the water pressure, so this is water pressure, will be gamma water times H water at point A. So how much gamma water? Gamma water, you should keep it in mind all the time, 10 kilonewton per cubic meter. So gamma water, if not given, so take it 10 kilonewton per cubic meter times how much is the water height? The water height here was 5 meter. So times 5 meter, this will give us the pressure of water 50 kilonewton per squared meter. So from this two, we can now find sigma dash, the effective stress, equal to 180 kilonewton minus 50 kilonewton equal to 130 kilonewton per squared meter. So this is the effective stress at point A if we have the water table at 5 meter. So this was our first requirement, you can see here. So if the water was at if the depth was at 5 meter depth. Okay, what is the second requirement? The second requirement is to find similar effective stress at A, but if the water table rises to the top of the soil layer, so the water height will rise from 5 meter to 10 meter. This is the idea in part 2. So we add another one. So for question 1b, so here is same soil, but we have the water table at top. The water table rises. So the total height of water is 10 meter. The water table is also 10 meter. Gamma soil or gamma bulk equal to 18 kilonewton per cubic meter. And we need to find the soil pressure, the effective soil pressure at A. Okay. So again, sigma dash at A will be equal to sigma A total stress minus UA. For sigma A, does it change or same value? Because the soil layer still same or the soil stress still same. So sigma A is equal to 18 kilonewton cubic meter times 10 meters, so equal to 180 kilonewton per square meter. For you, the water pressure at A has changed. So it's still gamma water times H water, but H water increased from 5 to 10. So this will be 10 kilonewton per cubic meter times 10 meter equal to 100 kilonewton per square meter. So sigma effective at A equal to 180 minus 100 equal to 80 kilonewton by cubic meter. Okay. Do you have any question about that? So this is the effective stress at A, and we can use this example to prove something we mentioned last week in the lecture last week, that based on our equation, okay, sigma effective equal to sigma minus U. Okay, when the water pressure increased from 5 meter to 10 meter. What happened to the stress, the effective stress sigma dash? Because the total stress is constant in this case, or didn't change. So what happened to the effective stress? The effective stress decreased from 130 to 80. So this should be kept in mind all the time. When the water pressure increase, what happened to the effective stress decrease? This means that the effective stress decrease means the effective stress decrease means the soil become weaker or stronger. So when the effective stress decrease, this means that the soil become weaker. So increasing or when the water pressure increase, the soil become weaker. Okay. So this is the first class activity. And if you have a question, guys, just let me know, please. Do you have any question, guys, about that? No? Can you mention in the chat if everything is okay or not? Okay. Thanks, Adrian. Okay. And this is our second activity. Thanks, Omar. Okay, so this is our second activity for today. We have another one. So in this one, we need to calculate the effective stress as well, sigma dash, and shear strength tau in the middle of the gravelly sand layer. Consider the water table to be at the ground surface. So the water table is here. Okay, and we have two layers, one 8 meter, one 6 meter. Gamma for the first layer 17 kilonewton, which is sandy silt, and the other one is 21 kilonewton per cubic meter, which is gravelly sand. And we need to find the effective stress somewhere here in the middle of the bottom layer. So at 3 meter. Okay, so this is the requirement of this example or this activity. Add 2 pages for that. Okay, so for question 2, we have this is our soil profile, 2 layer, 8 meter, 6 meter. This is the water table, and we need to find the stress at this point here at 3 meter. So this will be 3 meter, and gamma, let's say soil 1 equal to 17 kilonewton per meter, and gamma 2 or gamma soil 2 equal to 21 kilonewton per cubic meter. Okay, so how to find the first requirement, which is the stress at any point here or here or here, so point A, for example. So it's effective stress sigma effective A equal to total stress sigma minus U. So again, this is our formula for effective stress. So sigma dash effective stress, the requirement, sigma A total stress, and U is the water pressure. So this is our first requirement. How to calculate that sigma A? Sigma A is here. So the total stress will be the weight or the stress of this layer, this part 1, and the weight of this layer, so part 2. So we will have two components of stress. The first one is sigma soil 1 times H1 plus sigma soil 2 times H2. So sigma A will be 17 times how much the total height of the first layer, 8 meter. So 17 kilonewton per cubic meter times 8 meter plus this part, half of the layer, because we need to find in the middle of the layer. So it will be 21 kilonewton per cubic meter times 3 meter. This will give us the value of 199 kilonewton per squared meter. So again, we have two component of layer because we have two layers. Two component of stress because we have two layers. Okay. Any question up to here? So this is the only new thing in this example for the total stress. And now second step is UA. How much UA? UA is gamma water times H water above A. So above A. So how much is the water height? 3 meter plus 8 meter. So it will be total 11 meter. So it will be gamma water 10 kilonewton per cubic meter times 11 meter. This 11 meter comes from 8 meter plus 3 meter. So this equal to 110 kilonewton per square meter. So sigma effective at A will be 199 minus 110 equal to 89 kBA or kilonewton per squared meter. So this is the final effective stress at any point at the middle of the second layer. Okay. Do you have any question, guys, for that? This is the first requirement. The second requirement is a direct application on the shear strength. So we need to find the shear strength at the middle of the second layer, which is the gravelly sand. So requirement number 2, shear strength at middle of gravelly sand layer. This is the second requirement. What is the formula for the shear strength? Tau equal to C plus sigma tan phi. This is the shear strength formula where C in this formula is the cohesion, phi friction angle, and theta here is the effective. So we can add the dash here to make it more easy to understand. So sigma dash here is the effective stress of the soil. So from our first calculation, sigma dash at the middle of the layer was 89 kBA. So this is known from the previous step. Now, how we can find phi and c? Phi and c will come from the Australian standard AS 4678. So using the standard, you will find that phi equal to 35 degree and c equal to 0. Why c equal to 0? Because this layer is a sandy layer or cohesionless soil. So using these three values, tau will be C, which is 0, plus effective stress 89 kPa times tan theta, which is 35 degree. This will give us the value of shear stress as 62.3 kPa. So the final shear is this value, 62.3 kPa. Okay, do you have any question, guys, for this class activity or this example? Any question? No? Okay, so that's it for the effective stress. And the next topic will be the subsoil investigation. So I will just close this file. I can stop sharing. And if you have any question, just let me know, guys, please. Nothing yet? Okay, so our next topic is subsoil investigation. So can you see my screen now? This is our third topic for the substructure component. Thanks, Ammar. So we need to discuss some information about subsoil investigation. What is the importance of subsoil investigation and why we need to do subsoil investigation? So why subsoil investigation is important to us? Because we need to know the soil probabilities at the construction site before starting the design and construction process. So before you start the design of your building or your foundation of the building, you need to have some idea about what is the soil properties in this area, and if the soil, whether the soil is weak or strong. For example, if the soil is like loose sand or clay, not stronger like rock or dense sand or so on. So the type of soil will give you idea about what is the design strategy you will be using in your design. Okay, so this is very important to know the subsoil investigation or have idea about the soil you are dealing with. For example, if we have this soil profile somewhere in Christchurch in New Zealand, we have used this profile before in the previous lecture. But anyway, this is a good example of how the layers change in very close area. For example, we have two buildings. These two buildings are very close, not very far away. They are about almost 2 kilometers. So for example, this 2 point, building A and building B. And if you look at the soil underneath each building, what is the soil here? What do you think the soil here? Is it weak or strong? Here, this area, you can see there is sandy gravel layer, very strong one. So this is strong layer. And if you look at here, so if you take the soil underneath this building, so it is weak soil because we have sandy, silty sand, but here we have gravelly sand or sandy gravel. Okay, so in some cases, even within short distance, the soil properties can change much. That's why it is important to have better idea about what is the soil you are dealing with and have like detailed investigation of the soil layers underneath your building or in your construction site. Okay, how to get this profile? This is also one of the questions we will face. One of the methods you can do is a borehole. Like if we have, this is our soil, so we can have like a depth like that, borehole, with some method we will mention later. So this borehole will give us some idea about what are the layers. For example, this is one layer, this is another layer, and this is another layer, and this is another layer, and this is another layer. So we have, for example, the first 3 meter, one layer, second 5 meter, different properties. So using the borehole, you can identify the layers and then you can identify the properties of the soil. Okay. So the soil profile is one of the important things we are looking at when we are doing subsoil investigation. So now again, why we need the subsoil investigation and why it is important. The first thing is to discover the properties of subsoil, mechanical and hydraulic properties. Okay, so what is the mechanical properties of soil? The mechanical properties include the strength of the soil or bearing capacity of the soil. So all of this mechanical properties of soil are very important to us when designing foundation or footing. So these are important in footing design. Okay, what other properties we need to know? Hydraulic conductivity of the soil. Hydraulic conductivity of the soil means the impermeability of the soil or the speed or the how fast or the speed of water moving inside the soil or between particles. Okay, so this hydraulic conductivity or hydraulic properties are also important to know how fast the water move inside the soil between the particles. So we have some mechanical properties and some hydraulic properties. We need to know based on the investigation of the soil or subsoil investigation. Okay. Another thing is to assess the suitability of the site. So for example, if the soil is very weak, so we might be not able to build a house or build our structure here. Okay, so for some cases, if the soil is very weak, you are not be able to build your building on this type of soil, and maybe you need to remove the soil and replace it with a strong soil, and you have to follow another strategy, not just construct your building on this weak soil. So this also investigation of soil will be important to assess the suitability of soil. Also will be good to know the soil to have an economic and safe design. So as you know, the design should be or should satisfy two conditions: safety and economy. Not only safety or not only economy, so you have to, your design should be safe and economic. Okay, the soil investigation will help us to satisfy these two conditions, because when you know if the soil weak, so you will take this in consideration and design based on that. Also, when you know the soil type, so for example, we have two different type of foundation. We have something called shallow foundation and deep foundation. Deep foundation is very costly. Shallow foundation is more affordable. So based on the soil investigation, you can decide whether you have to use shallow foundation or deep foundation. For example, if you didn't do the investigation and just to go to the deep foundation, this will be a wrong choice because it will be more costly. Okay, also one of the importance is to reduce the risk and confirm the cost of the structure of the construction, so you don't have any extra cost after the proposal. And also this will give us better plans for our construction. What is the plan to do? Like for example, if as I mentioned, if you need to replace the soil or you have to compact the soil and so on. And also the subsoil investigation will give us an idea about what is the possibility of failure if happens of this building or this structure. So because you know what is the weakness of the soil, so you know whether this will cause failure or not. So all of this are importance of our subsoil investigation or our topic today. Okay, and if you remember in first lecture, we talk about the leaning tower of Pisa. And if you remember, this was the tower. So due to some soil movement here and the weight of the building, what happened to the building? It sink from one side or settle from one side. So the building has rotation and they have to move the weight of the building to keep it stable like that. Okay, so what was the problem here in this area? It was soil problem due to ignoring the subsoil investigation. Okay, so if you ignore subsoil investigation, this will be causing settlement of soil or even failure of building and will be very costly. Okay, so if you ignore the soil, the cost of fixing that will be more than doing the subsoil investigation before starting. So that's why we need to keep in mind that soil investigation is one of the important steps before starting the design or the construction process. Okay, here is what do we need to find out from or using subsoil investigation. what we are looking for from the subsoil investigation. We need to know the general distribution of subsoil layer. For example, again, this soil profile in Christchurch. Okay. So we need to know the subsoil subsoil layers. For example, we have silty sand, loose medium sand, dense sand, sandy gravel, and so on. So we need to know the layer because each layer has different geotechnical probabilities. And also using that, we will know the geotechnical probabilities of soil in relation to design and construction. Again, the geotechnical probabilities such as mechanical probabilities or hydraulic probabilities. Mechanical, the most important is the strength and bearing capacity. Hydraulic, such as impermeability of the soil. Okay, and these two types of probabilities will help us in the design and construction process. Okay, also will give us the ground water condition. So using the subsoil investigation, you will know what is the water level. For example, if the water level or the water table is here, how we know where is the water table using the subsoil investigation. Based on the water table, you can also know the effective stresses as we just do in the previous lecture. So again, this effective stress sigma minus U. U is the water pressure. So the water pressure also level is, or the water table level is also important in our design process. Okay, so the inside bore water pressure and surface water drainage, etc., is important for us in our building, or sorry, on our design or our construction process. Okay, and here, if you can see, in some cases, we can have information limited, some limited information. For example, this part, because we have a sandy gravel soil, so we cannot have uh, like we can't go deep in the soil in some cases. So we can sometimes here reach 15 meter, for example. And here in the other area, we can have the soil profile for maybe up to 25 meter. As you know, when you go deeper in soil, in soil layers, so it might be costly. So because you will need licensed people and special material, special machines to do the boreholes. So sometimes it's hard to find the probabilities of soil in very deep locations. So that's why the subsoil sometimes may be challenging because you don't have enough information due to the soil nature in the area you are dealing with. Okay, so this is the three general parameter we are looking at in the subsoil investigation. So the general distribution of subsoil layers and geotechnical properties of these layers, and also the groundwater condition or the groundwater level. Okay, what is the expectations from subsoil investigation? The expectation again is we need to satisfy the safety and economy of the design and construction process. So we need to achieve safety and economy. Also, we need to allow for reliable design and construction of structure for its design life. So we need also to achieve the design life of building. Because if you have an important building, for example, a library or whatever it's library, hospital, or any important building, so you are designing as you do in the superstructure component. So you are designing beam, rafter, and so on, and all of that will be supported by foundation underneath. Okay, so you need to make sure using the subsoil investigation that this foundation design or this construction is safe and economic. Otherwise, what will happen to the building? The building will have cracks and it might fail due to inappropriate investigation of the soil. So what we need to do using the subsoil, also we need to achieve safety and economy of the building design and construction, also to achieve the design life of the building, because as you may know that each building or any building to be designed has a design life or should live for certain period, or it's designed to last for certain period. For example, for the normal building like houses and so on, it is designed for 50 years. For important building or buildings that serve many people like hospital again and schools and so on, any public building, so it's designed for 100 years. So you need to make sure that the building will last for this period from the soil perspective. So you need to make sure that you know the information or the properties of the soil to achieve this target. For other type of building like road pavement, also we will be discussing the road pavement later in the course. So the road pavement is designed to last for 20 to 40 years. So you need also to make sure to achieve this. But in some cases, which is very rare and extreme cases, we need to design the building to live for thousands of years, because it is very dangerous building and we don't have the option to fail or crack and so on. Like for example, the radioactive materials storage or nuclear plants and so on. So this should last forever or almost like for thousands of years. Okay, but this just extreme cases we don't deal with oftenly. But this also you can have idea about that some buildings can last forever. Okay, but this only theoretically. Anyway, so this was the expectations of the subsoil investigation. And then what is the challenges we are facing when we are doing soil investigation? The challenge is if we have area of land like that, just one of the challenges. So you have very wide area, let's say 500 meter by 1,000 meter and so on. So if you will make a boreholes or whatever the soil investigation you will do, so you can have few points, like for example 1, 2, 3 points or 4 point, 5 point. So you will have just a few point, and these 5 points are not representative of the whole area. So you cannot find or you cannot do soil investigation for the whole area, because this will be too much work and too much money. So you need to just pick some points to study on or investigate. Let's make it hard have certainty of the results you got, but this is what is one of the challenges we are facing in subsoil investigation. So a typical investigation exposes between only 1.01 to 1% of the total area. Okay, so 1 meter to 100 meter per hectare. So we are only covering very small area of the studied area or of the site area. And also even lower proportion of the volume of the material is exposed or sampled, because what you get out of here, you will you will make some sample. These samples are even smaller, so you don't have enough representation of the soil. Okay, so we have seldom enough data for statistical analysis. Even so, we have to make the decision and recommendation. So this is what we have to do. So we have to take risk due to uncertainties when investigating the soil. Okay, so all the time you will not be able to investigate all the soil or all the site you are dealing with. So you will have uncertainties, and you will have to make risk and take the decision. Okay, so this will lead us to the next component or the next dot point we are dealing with, which is the risk components. What are the risk components we are facing in subsoil investigation? We have geological and soil materials are variable, spatially and temporally. So for example, if you have a wide area like this, so if you take soil sample, let's say each, whatever the distance is, 200 meter. So you have 1, 2, 3 samples, for example. So these 3 samples, the soil in this area and this area and this area are different spatially and temporally. Spatially means location, due to location, and also if you get to the soil to the site after 1 month or 2 months, also the soil properties will change. So temporary also changing with time. So the soil properties are changing with location and with time, which make it more complicated to study. Okay. Also, the spacing of the investigation location, as I mentioned, 200 meter, may or may not provide a representative picture of the site or some vital part of it. So for example, if there is different soil type here or different soil type here, so our 3 locations are not providing a representative picture of the site. So in some cases, your locations or your bore location will affect your soil investigation. But this also some of the uncertainties we got in soil or subsoil investigation. Okay, that's why we may have, we have also another problem is mistakes occur due misinterpretation of the ground condition. Okay, in some cases we have some misinterpretation of the soil profile or the soil properties. This is also one of the risks. Also, in some cases, we may have error in the reporting due to the previous step or the previous point, which is due to misinterpretation of the soil. which may lead to conflict or problems between the client and the construction manager and the engineers. Okay, so this also can cause or this one of the risks, some of the risks that we are dealing with, that because you are dealing with something inside the ground, so you don't have like much certainty about what you get. So this also can lead to some misinterpretation of the profile, soil profile, and cause error in reporting, which can lead to conflict between the client and the construction manager and engineers and so on. Okay, so these are some of the risk components associated with the subsoil investigation. And the next is, do we always need the subsoil investigation or not, or we can neglect or ignore it? We can mention, can we omit the subsoil investigation? In most cases, all sites must be investigated to allow, again, safe and economical design and construction. So this is the base rule or the basic rule that we should have investigation. But in some special cases or rare exceptions, where the risks are known and agreement or appropriate risk allocation is accepted by all parties, we can use the observational method. So only in some cases, rare cases, where the risks are known to all stakeholders, and risks are accepted between all of them. So you can use the observational method to just keep an eye on the soil properties and soil behavior. So this observation method will be used, but just need to have these two steps first. Identify all the risks associated with the project, and accept all the risks from all the stakeholders. Okay, this observational method will be applied or can be applied when the conditions are understood from previous investigation and experience. So from previous experience, maybe you have execute same building on same site or quite similar site before, so you know the risk and you already overcome the difficulties you faced before, so you can use the observational method. Again, all parties or all stakeholders accept the risk associated. Strategies for changed condition are devised before construction. So you have plans or strategies for any upcoming changes that could occur was or were devised before starting the project. This is very important one. Otherwise, conflict will be between the stakeholders. So we need to have strategies before starting. This will allow the prime cost sums for change it in cost in the future, because as you know, in the contracts you need, or the proposal, you need to define all the costs and all the element of the structure. So this element or this cost will not be considered, but it can be considered under the prime cost sums. So this is also need to be taken in consideration in this method. And the most important point is we need to have appropriate monitoring and supervision and inspection conducted during and after construction. So we need to keep monitoring the soil behavior during all the processes, during the construction, during the design, and even after construction. Okay, so this is the observational method and when to use it. Do you have any question, guys, for that? Okay, do you want to have a rest, a break? You can take a break. Let's get up again here. Okay, so we can have a 5-minute rest and start again. Okay, thank you. Okay, guys, are you back? Okay, thank you, Dayla. Okay, so now we can continue. The next point we need to know for the subsoil investigation is the stages of the subsoil investigation process. So we have few stages to to finalize our subsoil investigation. The first is disk study, and then reconnaissance survey on site, so site survey, ground exploration, laboratory testing, assessment and reporting, and then the final step is review during construction and keep monitoring the soil behavior. Okay, so we'll take the stage step by step. The first stage is the disk study stage. So this will be carried out at the start of the project or start of the subsoil investigation and before starting the design process or construction process. Oftenly during the proposal preparation of the project. The purpose of this uh, stage is to provide as much information as possible on probable ground conditions and likely problems before ground investigation work starts. Okay, so in the disk study, we're just making some maybe online search or all the project and so on to have just idea about the soil in the site. The soil on the site we are investigating. Okay, so we need to find the probable ground condition and likely problem we will face before starting the ground investigation work. Okay, what is the sources of information we will use in this disk study stage? So we might use Google Earth, which is a useful source for the soil layer and soil Like it will show the heights and the different levels of the soil, like mountains, hills, and so on. And also you can use the internet databases and also aerial photos. So you can have photo from top using aeroplane or drone or something for the location. The geological maps, also we have some soil map, topographic maps, other published information, for example, from local councils or governments, and adjacent site investigation. If there is neighbor or something and has already done the investigation, we can share the information with them. Mining records and from experience, background, intellectual property. Okay, so all these sources are used in the disk study stage. And here on the left, this is the SA soils map. So the colors given the soil type. So this area, for example, the red area, hard red soils, or hard yellow brown red soils, and so on. The shallow one or the sandy soil, shallow sands, for example, here, these areas. Okay, so there is a lot of valuable sources online, or for example, from neighbors that can be used to find the or to finalize the disk study. This we can call it as preliminary preliminary stage before going to the site. Okay, and here we have some example about aerial photos for one of the sites. So the aerial photos from top show the nature of the soil in this area. For example, this is a bridge project, and here is the location of the bridge from this area to this area. So you can look at what is the nature of soil in this area. For example, we have a river here, and we have some soil type here, some heights here. So this aerial photo can be considered as one of the sources to use in the disk study process. And this also another example, which is old reports. This study was an old study for the soil under Adelaide City or under SA in general. Okay, this also older reports may be helpful to show how the soil profiles has or have, sorry, changed over time. Okay, so let's say this is from 200 years or 100 years, and you are investigation now. So you're comparing now with the previous or in the future after 200 years or 100 years. So you can have idea about how the soil profile changed is in this area and how the layer was formed in this area. So this is also a good source we can use. And here is also an a section in the soil profile made by Oricon for one of the sites. So also this information can be used in the risk study stage. For example, if you are construction a building somewhere here, so you can use this profile to know what is the layers underneath the soil before going to the site and investigate yourself. So this all are some sources. And here in this link, if you open the link, click this link. This link is for For SA maps, just give all the soil in the soil types in the SA. This map is provided by SA government. I'm just trying to open the map for you. You can have a look on the map, and I'll just share my screen. Can you see my screen now? So this is the map provided by SA rig. So for example, if we are here in Adelaide, you can zoom out and see the soil nature in this area. Okay, so this also may be a helpful source for you to see before to look at in the study in the disk study stage. And if we return back to our slides, so the next stage or stage number 2 in the subsoil investigation is the reconnaissance survey on site. So this survey is just can be called as walk-over survey. So we need to go to the site and walk over, and usually carried out after the disk study and preliminary plans have been made for the ground investigation. So when we go similar to this person here, so purpose is to find extra information on the geology of the site, and likely if there is any construction problems we may face during the soil investigation or the construction. Assess the access for investigation plant and equipment. So we will also assess whether the availability of to use the machines or the tools in this site. Okay, so this also another important step in our subsoil investigation to collect the information from the actual size before starting the sampling and testing processes. Okay, we have note here that both the disk study and walkover survey provide large amounts of invaluable information with reasonable cost. The main advantage of that, it is very cheap option to find the information compared to the next stages. So they are by far most cost-effective part of the site investigation process because there are only maybe one person doing all of that on the disk and also on the site. Okay, but they are both only like a preliminary steps before going into detail on the soil investigation. So this is the main step, in the subsoil investigation, which is ground exploration. So we need to explore the site technically and get the samples and test them to finalize the subsoil investigation. In this ground exploration, our primary function is to successfully refine the geological model. So we need to refine the geological model of this soil. And this will include determining the lateral variability of the ground. Again, for example, if we have a very wide area, so we have different sample at different distance, for example, 200 meter. So this is what is called bilateral variability of soil. So the soil variability from point A will be different from point B. So we need to check how much is the variation if we move laterally. Also of obtaining vertical profiles. So we also will have to do another point, like maybe a borehole or something, to see how much the soil change vertically as well. So we need to know how much the soil varies horizontally and how much the soil varies vertically. Okay, this will include determination of the water ground condition. For example, if the water ground here, so we will know using the vertical profile. Collection of samples for laboratory testing. So we also will have some testing, like again, to measure mechanical and hydraulic properties. Locating specific targets such as the extent of rock or fill, subsurface voids, for example, in abandoned mine working. So in some soils, you will have a fill layer which you cannot put your building on. So you need to know this fill, or if there is rock, also need to know where is the rock, because if there is a fill here, so you need to remove this layer and add or replace with a different type of soil. Okay, replace with a stronger soil. So this also will be in under the ground exploration stage. Okay, the ground exploration stage will require depth of the vertical profile and also spacing between the boreholes or the sample location. So we will have, if we have one here, one here. So we are looking for how much is the distance x and how much is the depth z. So we need to know these two information, the spacing and the depth of the borehole if we are making a borehole. Okay, and this is a funny figure showing that the importance of the distance between the borehole. For example, if we have borehole here and we did the borehole, so we have avoid a lot of all of this underground. So we have missed this one, maybe this a bullet or something, and we have missed this one, and we have missed this fill. So in only one borehole can miss a lot of hazard inside the ground. Okay, so there's just a funny uh, image to show that one borehole will not be enough to represent the soil behavior or soil layers in our site. Okay, so this is the depth and the spacing guidelines for ground exploration. Ground exploration. So the depth and spacing depend on the structure to be built and its location. So the number of or the spacing and depth of the boreholes can depend on the structure, type, and location. For average house, we need 3 boreholes from 3 to 5 meter depth. So if you are building a house in one location, so you will need 3 boreholes at 3 to 5 meter depth. Okay. And this table give us a guideline for what is the spacing of the boreholes. This only a guide, again, a guideline, not a fixed number. So you can maybe increase or decrease depend on the conditions you have in your site. Okay, so for high-rise and industrial structure, from 50 to 40 meter between the boreholes. For dams and weirs, from 25 to 75 meter. For some special structures such as bridges, stakes, machinery, foundation, from 2 to 6 investigation points at least per foundation. So depend on the type of structure, the spacing will be decided. And here is more specific, or sorry, more information about the depths. So here we were taking in this slide about the spacing. in this slide we are working on spacing, and in this slide we are looking at the depths. Okay, so for the depths of investigation, we depend on the foundation type and structure being supports. The foundation type again can be shallow foundation, like footing, and the other type is deep foundation or piles. We will discuss the foundation later in the course. And here is some example. For example, if we have shallow foundation or high-rise building, so the depth will be more than 6 meters or 3 times BF, where BF is the width of the footing. This footing type is called strip footing, and it is one of the shallow foundation we have. Okay, BF is the width, so the depth criteria ZA underneath the which is underneath the footing, or this is called foundation level. So ZA from this point should be more than 6 meters or 3 BF. We will take the greater of them. Okay. For linear structure like roads or airfield should be more than 2 meters. For example, this one here, this is a road. For linear structure, canals or pipeline like this one, so it should be more than 2 meters or 1.5 BAH, where BAH is the width of the canal. Pile foundation or deep foundation, it should be more than 5 meters or 1 BG or 3 DF underneath the pile, starting from the pile, below the pile, where BG is the pile group width. We will know that later. Or DF pile diameter. Okay, and so on. So this table also a guideline for how much the depth required underneath or depth required for the exploration process. Okay, the next step is what is the methods we are using for ground exploration process. The first one is called test bits. We have also drilling, we have in situ testing, and we have geophysics. Geophysics is not very common procedure, so we will just know the name of it. But other three we will go into details. Okay, what is the test bits? Test bits is one of the ground exploration techniques we are using, which means that we are opening or making, if this we're making hole in the soil, if this is the soil, so we are digging a hole and get into it, the hole to get the properties of the soil or to know the layers of the soil. So bits, large bits, test bits means we make large holes into the soil to investigate the soil. The problem, we have some problem in this soil that we need to retain the wall. If you can look here, we have to retain the wall, and this will be using some retaining wall techniques. Otherwise, the soil will fail. Okay, so this will limit this will limit this method limitations due to retaining wall requirement. Okay, and also it will not be not very safe because you are under risk of soil failure at any stage. So that's why uh, it is not the safest option to do the soil or the ground exploration. Okay, as you can see here, also you cannot go very deep. Sorry, you cannot go very deep because if you go more deep, you will it will be more costly because you will need the retaining wall. Okay, so you have a note here that never enter a trench or bits more than 1.2 meter deep without supporting the stabilizing the site. Or we can mention retaining the walls of the hole. Okay, so this is the limitation of the methods, and here some advantage of the methods. The advantage of this method, it is a good method for obtaining detailed info on strengths. So this will give us much info about strengths, but only for very limited, if this is the soil, so for only limited depths. We cannot go further, so maybe 3 meter maximum, 2 to 3 meter maximum. And we will get also stratification, information about the stratification or the strata of the soil, and pre-existing shear surfaces and discontinuities of the soil. So if there is any discontinuity in the layer, so this will be shown in the test bed. We will also get very high quality block samples can be taken from the soil because you can, you can see what is the soil you have dig out, and you can uh, make very high quality sample from that. Okay, equipment and personnel needed in this method are generally available at reasonable cost, so it is also economic option. Okay, so all of these are some advantages of the method. The disadvantage of this method are that test bits must be backfilled. So you need to fill if you have dig a bit here. So you need to fill it again with the soil. Okay, and you need to compact the soil again. Otherwise, it will affect the properties of the soil. Also, confine the space working. The space is not enough to work from heights restriction may apply. Okay, so due to limited height, you will have limited space to work. So this all are disadvantage of the method, but it is a good method to investigate the soil near the ground surface. So this might be the best option if you want only to investigate the soil near the ground. Okay, so this is the first step. The first method. The second method is our main method, which is drilling or boring. We have several methods of drilling or boring, which will give us bore holes or bore plugs. This is very common method. to get the soil layers and soil behavior. So we have cable precaution drilling, and we have some augers to dig in the soil. So the this method we will make very narrow holes using the augers to dig and to extract the soil. Here is some videos on YouTube about the drilling techniques. You can have a look on that to watch the videos. And this also another method if you are going more deeper. Which is core drilling, which is also one of the drilling techniques. And here is some advantage and disadvantage of the drilling and boring method for ground exploration. So the drilling allows sample to be obtained from greater depths. Again, you can go very deep in the soil. For example, 15 meter, 20 meter, and so on. So depend on how deep you want to go, you can go, but might be very costly if you go very deep, like up to 25 or more. So this is one of the advantage. Also, this will minimize the disturbance to the ground, again, because this hole diameter is very narrow, so it will not cause disturbance to the soil. Okay. Also, we can proceed in conditions that pre-load test bits, both very hard and very soft ground. For the bits, if the soil is very hard, so you might be hard to dig inside very hard soil. But for the drilling or boring, it can proceed in these conditions. So the drilling can overcome the difficulties facing the bits, the soil bits or testing bits conditions, and also generally quicker than test bitting because less digging because it is very small diameter. Okay, but there is also some disadvantage of this method, which is need specialist equipment and personnel are required, which is very costly. So the only problem is the cost and the speciality required for equipment and personnel. Okay. Okay, I think we can stop at this point today. Do you have any question, guys, for today's lecture? Do you have any question? Dylan and Okar, do you have any question, guys? Okay, thank you, guys. Thank you, Okar. Thank you, Dylan, for staying to the last, and thank you all for attending today. And next week we don't have lecture because it is public holiday, so we will meet the week after next week. Okay? Thank you guys and see you. See you. Bye.